In Chapter 25, we are dealing with a different type of reaction mechanism, one that involves single electrons at a time, that is, radical intermediates. There are two major types of reactions and 5 specific examples that I'm going to highlight in this video. The first of these is a reaction in which one of the hydrogen atoms on carbon is replaced by a halogen. This is a way to functionalize alkanes that have no other functional groups, and it is the subject of Chem Activity 15. The second reaction also involves a radical halogenation, but specifically at an allylic position. Recall that at an allylic position, that is a position of a carbon that is sp3 next to a pi bond. There's also benzylic positions, which are next to the pi bonds of benzene rings. And either one of these can be replaced by a halogen, specifically bromide, with a very specialized reagent. That reagent is called N-bromosuccinimide, NBS, and it produces very low concentrations of bromine in solution. The third major example of a radical chain reaction mechanism is one in which we do an addition of HBr across a pi bond, but this time we're doing it in the presence of peroxides. And we end up with a bromine and a hydrogen added across a pi bond, much like we did with an ionic mechanism way back in winter quarter. However, now the regioselectivity is reversed. That is, the H goes to the position that initially has the least H's. The fourth reaction is actually out of Chapter 26, which was your reference chapter for following your last midterm. And that is a mechanism in which double bonded things like styrene can polymerize under radical conditions. Notice again we have the peroxide initiator to start the radical reaction. We end up with a polymer that has been created through a radical chain process. All of these reactions do involve a radical chain mechanism, and in the Chem Activity 15a, we look at the radical chain mechanism for the halogenation process. Since it has an intermediate radical, the radical character determines the selectivity. When the CH is attached at an allylic or benzylic position, this reaction is more rapid, hence the reaction of NBS at an allylic position selectively. Bromine in general is quite reactive towards tertiary over secondary over primary, or allylic or benzylic over secondary or primary. Chlorine is somewhat selective, but will still do the reaction. Iodine and fluorine can theoretically do this reaction, but iodine will not because the chain propagation steps occur in an endothermic pathway. And fluorine, it's not practical. The last two reactions in the chapter go by a somewhat different mechanism. Both provide new synthetic. For example, if we start off with an alkyne and we want to make a transalkene, up until now we have no way to do that. The second of these two reactions is a way to remove one of the pi bonds from benzene to give us an unconjugated cyclohexadiene. Both of these occur in the presence of an alkali metal, often lithium, and a proton donor. In the case of the alkyne to transalkene product, the proton donor is also the solvent, liquid ammonia, cools to a liquid at -35. And in the case of the reduction of benzene to a cyclohexadiene, proton donor is an alcohol. These two reactions are both reduction reactions, and they happen much like reductions in most biological redox systems. That is, an electron is transferred from the metal, followed by a proton from the proton donor, followed by an electron from the metal, followed by a proton from a proton donor. So, for example, this triple bond is reduced to this double bond with 2 lithiums and 2 ammonias. So altogether, we have 4 examples of reactions that occur by a radical chain mechanism and 2 reactions that occur by electron-proton pathways. I'm going to give you one example of each mechanism. Since you will be working through the mechanism of the alkane halogenation during the chem activity, I'm going to work instead on the radical addition to give anti-Markovnikov addition of BRH.